Hello everyone, thank you for joining my presentation. My name is Neha and this is my final project for the CMP 7005 from data to application development. I focused on the critical environment issue of air pollution, specifically analyzes PM 2.5 levels. My aim was to develop data pipeline from raw dataset handling to exploratory analysis to predictive modeling and developments in a user-friendly dashboard. So the first one is data handling. The data set used by the sourced form of UCI machine learning proprietary. Initially pre-processing included merging dataset, handling missing values and praising data time feature using pandas. I identified and removed incomplete records and converted relevant columns to proper format to make it ready. I engineered additional features such as extracting year and months from timestamps. The step in secure data integrity reduced noise and enabled accurate model training and clean visual output. The next one is exploratory data analysis. To explore the pattern and relation within the data, I performed multiple visualization using Seaborn. So the another one is correlation heat map. So the next one is correlation heat map, and in this particular map the correlation matrix focused on numerical features only. PM 2.5 had a strong correlation with PM10, NO2 and SO2 pollutants commonly associated with traffic and industrial activity. This helped identify the most promising feature and prediction. The next one is scatter plot. This will explain the scatter, the wind speed, and the another thing. A scatter plot visualized the inverse relationship between wind speed and PM 2.5. High wind speed tends to disperse pollutants, resulting the cleaner air, an important insight for seasonal and weather aware models. This visual provided clarity on temporal and spatial variation in pollution, informed the feature selection and shaped the prediction logic and next phase. The next one is box plot by station. I created box plots comparing PM 2.5 level across station. Dongsai and Guinan consistently showed higher medians, indicating central areas are more polluted than outskirts like Huayu. The next one is predictive modeling. So in predictive modeling, I used a linear regression approach to estimate PM 2.5 concentrations based on other pollutants and meteorological features. The selected features include PM10, NO2, SO2, COO3, temp, pressure, DWAP, rain, and WSPM. They were standardized using scikit-learn's standard scaler to improve model stability. The model was trained and tested on the same dataset initially to validate feasibility. I then plotted predicted versus actual PM 2.5 values to assess performance. The feature conflict scenes were also displayed in the app. While not the most complex model, this baseline approach served well for demonstrating explainability, efficiency, and real-time application integration. The another one is Streamline Application GUI. To make the project interactive, I developed a streamline-based web application titled Beijing Air Quality Analysis Dashboard. The app features three sections. Number one is Data Overview. This includes a preview of dataset, column insight, summary, and missing value report. Number two is EDA. Here, users can view dynamic plots like PM 2.5 histogram, correlation heat map, station-wise box plot, and winds versus PM 2.5 scatter. The another one is prediction model. This section demonstrates the linear regression model. Users can see actual versus predictive PM 2.5 trend. Deploying this as a worker prototype ensure not only technical completion but also user accessibility, a key learning output of CMP 7005 module. The another one is reflection and recommendation. This project provided a well-rounded learning journey. I strengthened my Python skills, particularly in data handling and visualization. Streamline was a new technology for me, but I learned to build, a deploy, and fully GUI within a short time frame. The biggest challenge was aligning the machine learning pipeline with a dynamic dashboard, especially managing dependencies between clean dataset and act outputs. I also improved my debugging and critical thinking skills through troubleshooting models for errors, formatting issues, and environmental compatibility. Overall, the experience helped me connect theory to real world application, and I now feel more confident in full stack data development from raw CSV file to polished user facing app. The another one is version control via GitHub. Throughout the development process, Git and GitHub were used for version control. The entire project, including notebooks, app, and README, the hosted in a GitHub repository. This allowed me to track changes, test new ideas safely where reverting become essential. My commits were structured and descriptive, helping the clearly and the reproducibility aligning with the best practices in collaborative software development. Conclusion. To conclude, this project was a deep dive into data-derived problem solving, combining statistical analysis, predictive modeling, and interactive app design. I successfully transformed raw air quality records into a functional tool that offers insight into pollution patterns and predicts PM 2.5 level. The project not only fulfilled the academic requirements but also demonstrated the social relevance of AI in environment modeling. I look forward to building on these skills in future roles where real-time data, user accessibility, and public impact come together. Thank you for your listening.